Thank you very much. I have no conflicts to declare. So let's begin by thinking about image reconstruction in its most fundamental form, where an object gets encoded into a representation in a sensor domain. For PET and CT, that might be radon sinogram. For ultrasound, element time space, and for MRI, our familiar K-space, which is then reconstructed into an image. This recon, of course, can be very simple for fully sampled Cartesian K-space, in which case we just invert the Fourier transform. But more difficult acquisition schemes, like using non-Cartesian sampling, requires additional steps like regridding and density compensation. With parallel receive, even more sophisticated processing. And with incoherently understable data, we have to use, of course, advanced compressed sensing techniques. So what we have here are a bunch of disparate and very specific modular processes, each handcrafted to solve some problem that a new acquisition scheme has introduced. And until recently, this handcrafted strategy was also prevalent in other fields, such as speech recognition, where experts used to have to devise specific signal processing techniques for best representing acoustical elements. But we got far better results, as we've all seen from our phones, and et cetera, after transitioning to automated feature extraction, where we let the data define its own representation through a structured training process. And it turns out that this type of data-driven training is a huge part of how we learn to see as humans, a cognitive development process called perceptual learning, the refinement of perception based on exposure to and training on stimuli. So how we reconstruct our neural signals into the final percept image is a trained process, and it's been shown that it's this training that allows us to resolve incredible detail even in low SNR conditions, something that non-biological imaging systems such as MR often have difficulty in, as we'll see more of. So in the same way that for our vision, we get from the sensor domain of neural codes to the final image with data-driven training, our idea is to do that with MRI, going from the sensor domain of K-space directly to the reconstructed image with the same type of data-driven training. So for the rest of the talk, I want to describe this new formalism, what we call AutoMap, automated transform by manifold approximation. We recast the image reconstruction problem end-to-end as a supervised learning task and let the reconstruction relationship emerge from real-world K-space and image data. AutoMap learns the optimal function from scratch, having only the data to guide it. So for example, it doesn't even know what the Fourier transform is or that there even exists any representation domains at all. Specifically, we implement AutoMap with this deep feed-forward neural network architecture where during training, we feed pairs of K-space and their corresponding images and adjust the network parameters to minimize the error between the network output and the targets we give it through backpropagation. The complex sensor data is first input into the fully connected layers, which are essentially just matrix multiplications followed by a nonlinearity, such as sigmoid or hyperbolic tangent, which is what we use. And these layers are important because they perform the bulk of the domain transform approximation. And when constructed properly, they've long been known to be universal function approximators. Like their name suggests, they can approximate any function on a compact set with finite inputs and outputs within a provably small error. And then the convolutional layers form an autoencoder that forces the reconstruction to have sparse convolutional features by imposing an L1 norm penalty on the feature maps here. So instead of assuming a generic sparsifying transform such as the wavelet domain, we learn a more optimal sparsifying domain during training with a joint optimization. So for example, once trained, the network builds up the image from these sparse convolutional kernels that emerge and that you may have seen before as the receptive fields of the visual cortex. So after the whole network is trained, the reconstruction is simply a super fast feed-forward process on the order of milliseconds. So given this network, the very first thing we tried was to see if AutoMap could learn the most basic reconstruction scheme, the inverse Fourier transform. The network was trained on pairs of sensor and image domain data. The image domain were natural scenes from ImageNet, which are pictures of animals and trees and houses as seen here. And the sensor domain is a Fourier transform of each image. And we intentionally chose a very broad class of images to train on to avoid any overfitting concerns. So after it's trained, what happens when we give it the K-space of image it's never seen before? Here's the original image, the exact inverse Fourier transform looks like this, and here's how AutoMap reconstructs it. So this is pretty remarkable. You know, most of us, we've been playing around with Fourier transforms for a while, and so maybe it's hard for us to appreciate this, but this network learned a double integral of complex exponentials from scratch using only a relatively small set of examples to guide it. And of course, if we feed the network of a K-space of a brain, it reconstructs faithfully. Remember, it's trained on trees and dogs and such, and it's never seen anything close to a brain before or any in vivo data whatsoever. Okay, fine, you might be thinking that's cool and that's fancy, but we already know how to do a Fourier transform. So what? Well, because it can learn the Fourier transform, which is essentially an arbitrary encoding, it can learn other encodings too, and even beyond Fourier. And in those more sophisticated acquisitions are where AutoMap actually shines the most. Secondly, AutoMap doesn't actually learn the exact Fourier transform. Like the perceptual learning we saw earlier, it conditions the reconstruction on the features of the data, making it potentially more robust to noise. So to evaluate these claims, we take in vivo images, encode them into various K-space representations, and we corrupt the K-space with additive white Gaussian noise at various levels, and then compare how AutoMap and a conventional technique reconstructs. So let's take a look first at a spiral acquisition. Here we show a T1-weighted MP-RAGE as a reference. We re-encode this as a 10 interleaf variable density spiral with 25 dB of additive white Gaussian noise. And we can reconstruct this with a well-known conventional technique, conjugate gradient sense with non-uniform FFT regridding. And we see decent reconstruction here, but certainly there's also a substantial presence of ringing artifacts that have been amplified by the iterative CG optimization as we kind of saw earlier. And here's how AutoMap reconstructs it. Not only does it do the reconstruction at all, which is a feat unto itself, but it does it better without these ringing artifacts and a mean squared error of about 30 times lower. Now let's take a look at a completely different encoding, non-Fourier radon projection imaging with an SNR of 40 dB, a standard iterative technique employing the Kazmar's method. Doesn't do so well, a lot of white noise obviously. Not so with AutoMap, 80 times lower MSE. Now if we do an incoherent Poisson disk undersampling, SNR 30 dB, and reconstruct with compressed sensing from the BART toolbox, again, we get decent results, but it is quite a bit noisier compared with AutoMap. In fact, susceptibility to noise for compressed sensing is a well-known issue that is an active area of research, as you may know. Finally, we show a different class of difficult reconstruction, misaligned K-space lines you might have due to hardware miscalibration. It conventionally results in a ton of aliasing artifacts, but AutoMap compensates for them no problem. Now remember, all of these were trained on the same network architecture and hyperparameters, which shows the very flexible and generalized reconstruction capability of AutoMap. So to learn a new reconstruction for a particular encoding, one only needs to generate training data with the already known forward encoding model. Another important note is that none of these were trained with any sort of additive Gaussian noise, so there wasn't any noise modeling going on for noise suppression. Instead, what was happening is that AutoMap is learning the low-dimensional manifold of the data and thus finding robust representations of the signal, which would benefit the reconstruction from any sort of small undesired perturbations. So let's investigate this feature extraction a little further. In the deep learning community, one common way to assess the feature extraction ability of a network is to observe the activations of the hidden layers, where the intermediate representations are. For us, the hidden layer in the fully connected section is of primary importance since it does the bulk of the transform function approximation. So with our network that was trained on generic images, this is the activation of the hidden layer. It looks like this if you feed the K-space of a brain through. Here it is again. Now, we could have trained the network differently, purely on the Fourier relationship by just giving it random noise inputs and the Fourier transform of that noise. And it'll still reconstruct an image accurately, but its activation map looks like this, much less sparse. So it's far less immune to noise because it's not taking advantage of features of real-world images. Conversely, we can go the other direction. If we train the network on a bunch of brains, the hidden layer activations are far more sparse and extracting far more relevant high-level features. Another way to visualize this is with the T-distributed stochastic neighbor embedding, or T-SNE, dimensionized reduction technique, where we visualize the relationship between the network weights. So this is a whole field in itself, but the key takeaway here is that training on real data results in a network that respects the local spatial correlation that exists in real-world images, where weights to neighboring pixels are more similar, adding redundancy to the network and is thus more robust to noise. So in conclusion, we've developed this new paradigm for image reconstruction, AutoMap, a unified reconstruction framework employing universal function approximation and manifold learning with deep neural networks to automatically learn the optimal reconstruction function for arbitrary acquisition strategies without any imposed expert knowledge. We've demonstrated robust immunity to noise, surpassing conventional techniques, and this means faster scan times like less averaging or higher undersampling factors. And again, once the network is trained, because the network is feed-forward, we have rapid non-iterative reconstruction on the order of milliseconds. Perhaps most exciting, because of the flexibility and generalized nature of AutoMap, we anticipate brand new acquisition strategies unfolding as researchers now don't need to manually devise corresponding reconstruction techniques. I'd like to acknowledge these funding sources below, and I also want to advertise for a talk we have on related work with deep learning for MR fingerprinting that's happening tomorrow at oral number 0688. So thank you very much for listening.